Differentiation under the integral sign, also known as Feynman's trick, is a method used to evaluate complex integrals. But before we can go over that, we need to touch on the Leibniz integral rule, which tells us that we can swap the differentiation and integral signs in expressions like these. Keep this in mind for the future. So here's the integral we are computing, and this is what it looks like on a graph. We can introduce a parameter r and make this a function of x and r. Here's what that function looks like as a 3D surface. So here's our function of r, and let's take the derivative with respect to r. Now we can use the Leibniz rule from before to swap the derivative and integral signs. And since the derivative is with respect to r, this sine of x over x is treated as a constant and can be pulled out. We could differentiate e to the negative rx using the chain rule, and now the x's cancel, and we can get rid of that negative by switching the bounds of the integral. We can evaluate this integral with integration by parts, and I've put the formula in the top right. First, we set u and v prime, which allows us to find u prime and v. Now we can rewrite the expression like so. We have another integral on the right side, which we can evaluate using integration by parts again. We set u and v prime, find u prime and v, and now we have an expression for this integral too. Notice this integral on the far right is the original integral we were trying to evaluate. Now we can distribute the r, and putting the integrals together allows us to factor out r squared plus 1. Dividing by this on both sides gives us an antiderivative, and now we can plug in the bounds. I'll plug in the infinity symbol as a shorthand for the limit as x goes to infinity. Most of these terms simplify to 0, leaving negative 1 over r squared as the derivative of f with respect to r. We can integrate this with respect to r to get f of r equals negative arctan r plus c. All that's left to figure out is c. We can take the original definition of f and equate it to the new definition, and then take the limit as r goes to infinity on both sides. This tells us that c is pi over 2, so f of r is negative arctan r plus pi over 2. We had originally wanted to evaluate the case in which r was 0, so our final answer is given by f of 0, which is pi over 2.